So last we left off. So here we are. This is 02 Flight Instruments, part 4 or 5. It's part 5. I know it says part 4 on that piece of paper, but this is the 5th day. So this is the 5th day. Don't worry, online it will say September 27th. So the last thing we did was take a really good look at just a very few items on an aviation navigation chart. So I want to see if it'll let me do it. Let me do it. So there on this slide that we were looking at, there's this dotted line, and you don't remember from the other day, but you'll probably write it down now. This is an isogonic line. Is isogonic anywhere on that L-I-N-E? Does anybody remember what iso means? I don't know if it's Greek or Latin. What? One, yeah. If you're standing anywhere on that line, at any point on this one line, there is one magnetic variation. In this case, it's 13 degrees east. And for those of you that weren't here yesterday, this chart right here up on the screen has Reedley International Airport on it, which is right there, and Fresno Air Terminal. Question, Jonathan? Yeah, you're welcome to do that. Thank you very much. Thanks for asking. So since we're looking at the isogonic lines, let's look at this chart of the United States. Now this isn't quite what this shows. Look at this. This shows 15 degrees right here. That tells me that maybe this chart is really, really old. So here's one thing about the magnetic North Pole: it does not stay in the same place. It moves. In fact, it's starting to pick up speed and move faster. It's moved faster in the last 10 years than it moved 10 years before that. So it used to be on Bathurst Island up there in northern Canada, but it's on a different island now. So on the chart today, it may say 13 degrees east, but if you pick up a chart from 5 years ago, it might say 12.5 east, and 5 years before that, it might say 12, because the magnetic poles of the Earth are moving very, very slowly. And so the magnetic variation doesn't stay absolutely the same. What's interesting to note is that the runway numbers are aligned with magnetic headings, but if they draw the lines and write a 33 for heading 330, and then over a decade, the magnetic lines of flux of the Earth moves, you may have to line up to 350 to land on the runway. And it's not in their budget to repaint the number, so they just keep calling it runway 33. All right, so you'll notice what's interesting. If these are isogonic lines, and I'm standing right here, we'll say I'm right here, and I'm not going to draw Kentucky, because I know Kentucky isn't Kentucky. There we go. If I'm standing on this isogonic line that relates to 0 degrees east, it's also 0 degrees west. That means that the straight line to the true North Pole is actually the same straight line to get to the magnetic North Pole. So if I'm anywhere, so you could argue that if you're standing on this line, there is 0 lines of magnetic variation. Out here, it's really sad. Out here on the west coast, we have east magnetic variation. But look out over here, this is the opposite. This is actually west magnetic variation. All right, so there's this saying, and it goes like this. It says, east is least. And what that means is, if I point at, let's say, a heading of 010, true, you notice the word says least? I would subtract 13 degrees if I'm right here, where it's 13 degrees east variation. I would subtract 13 to get my magnetic. So this east, though, is not talking about whether you're on the east coast or the west coast. It's talking about that E on the chart here. It's talking about this E right there. So if you're in east variation and you've measured a true course, east is least. So you take the true, you subtract 13, and that gives you magnetic. Question? Yes. East is least and west is best. So if you were over in New Jersey and you had west variation, you'd measure the true, and then you'd add the westerly variation that you're in, and that would give you the magnetic variation. And you're going to do this when you're planning cross-country flights. And the reason I'm saying that at the moment is because on this chart, and we looked at them very rapidly last time, is this straight line right here, going up right here, and this straight line going up right there, that goes to true north. And this one points at true north. So if that's going straight up, and we decide we're going to go from here, and we're going to go straight that way, we would measure this angle, and that angle would be 90 degrees, but it's 90 degrees true. So now the question is, what do we need our compass to say when we're flying? We need it to say 13 degrees different. And since this is east, east is least, we would take this 90 and subtract 13, and that would give us 77 degrees magnetic. So then when we took off and flew, if we wanted to fly straight, and some people would call this due east, if we wanted to fly 90 degrees true straight to the east, our compass would read 77. The good news is we're only going to calculate this on the ground. You almost never do this in flight, because once you're in flight, you do everything magnetic. Did I lose anybody? This is a good time to ask any questions. What's the point of doing it on the ground? Well, you have to decide before you take off. You want to know which direction do I fly. Let's say that's Vegas. And let's say we take off out of Selma International Airport. And the heading, the true heading is 090. But we can't fly that on our compass, because our compass is off by 13 degrees. So we calculate on the ground where it's simple, and we can get coffee and orange juice and watch YouTube videos and have a nice light, and it's not vibrating and it's not noisy, and I don't have passengers asking me where the throw-up bag, the vomit bag is. So we do this on the ground where we have plenty of time and we're not distracted. And then on our piece of paper, it'll say, take off and fly 077. So as soon as we take off, we get 500 feet off the ground, and we make a turn. We turn till the compass says 077, and we go, woohoo, Vegas, here we come. So we want to calculate that before we need it. But the nice thing is now the compass, and there's other things we're going to get to, they're all set up on magnetic. So our pre-flight planning, we're going to do everything that we're going to convert it into magnetic, and then leave it in magnetic the rest of the time. So what we're going to do before this semester is over, we're going to do that. We're going to actually plan a cross-country flight. I'm going to get a few more charts. We're going to go in the computer room where we have tables to work on, and we're going to measure. We're going to say we're going to take off from Selma International Airport, and we're going to fly to San Francisco International because we want to go to San Francisco, a 49ers football game, and we're going to land in San Francisco. Has anybody ever flown to San Francisco International and gone to a football game or a baseball game? I've only done it, I've flown in there 3 times. Twice I've flown in there to go to baseball games, making the other people in the airplane help me pay for the airplane. And then we took a taxi to and from the ballpark. And everybody else drank beer and had hot dogs. I had Coke and hot dogs because I was flying the airplane. All right. So here's just a completely different way. So look, it's a compass rose. Ta-da! But the numbers here, you see north, all these letters around there, those are all in magnetic. And this is so... Here, I'll ask the question. Don't say the answer until I call your name. Is this compass rose, is it in a place that has easterly variation Or is it in a place that has westerly variation? Jonathan Flores. Yes. How do you know that it is easterly in a place that has easterly variation? Where do you start? You start at true north, and you have, in this case, although it doesn't say 13, that's fine with me, you're saying you would have to turn yourself 13 degrees towards the east to find the magnetic North Pole. And that's what we talked about outside about 12 minutes ago. So all this time we've been talking about magnetic variation. So if you wanted to say, what is magnetic variation? You would say magnetic variation is the difference in degrees between true north and magnetic north. It's the difference between true and magnetic. And if I start an isogonic line, it'll be at 13. But if I fly somewhere it's 15, the variation will be 15. You could also look at it like this. Where could I find out, as a private pilot, where would I find out where the magnetic variation is? So let's try, see if I can call Jonathan's name again. No, sorry, Luis. Where would you look as a pilot if you wanted to find magnetic variation? I'll give you a hint. We looked at it yesterday. You know what that thing was that we had? What was that thing that we were looking at yesterday? It was a map. We tend to call it a chart. A chart and a map. Finger on it. I think San Francisco International is on the other side. So that would be an easy place to look. There's another place to look, and you don't have to write it down, but another place would be if you looked in the digital chart supplement and you looked up an airport, you looked up Selma Airport. On that, and I don't have a picture, on Selma Airport, it would say what the variation was at that location. So we already talked about that stuff. And so, wow, look at this. Look at this middle one here. Let's look at this last one. We just did that. If you start with true course or a true heading, we'll get to the difference between headings and course. If you're aiming straight true and you either add or subtract the variation, you end up with magnetic. So we've already done that. Yay. Deviation is a second type of error. And so I want to talk about being a deviate. So you probably know somebody in your neighborhood that when they moved in, they had to go knock on all the doors in the neighborhood and tell everyone that they were deviating from the norm. I'm making a joke and nobody's laughing. Okay, fine. I was talking about being a deviant. The deviation that we're talking about here is an error in magnetic constant. Let's think about this for a minute. So don't answer the question until I call your name. You get into an airplane with a compass, and you're flying at night, and you brought a flashlight that was stuck to the side of your refrigerator because there's a magnet on your flashlight. And you set your flashlight up on top of the instrument panel next to the compass. Apply something that I haven't told anyone. You have to understand the theory of a compass. Work. Yes, that's correct. It's not going to give you the right direction. It's not going to read the correct. It's going to be attracted or repelled by whichever. It's called magnetic deviation. To read. Going to write that down. It's something in the airplane, or it's something near the airplane. A magnet. It's something magnet. It's a magnet of some kind. So I suppose if we were writing up a movie script and we were writing in there, you know, and it was an X-Men movie and Magneto, what do you think would happen to the airplane? I guess if he turned off all of his powers, it'd be okay. But if he did anything, it'd probably make the compass operate. Questions, Jonathan? I have not researched the Bermuda Triangle to answer that question. No, but who knows? The gas comes from underneath the ocean, burns the whole airplane up, and it bursts into flames and breaks into 1,000 pieces, and then at the bottom, and nobody ever finds them. So far, that's my most plausible explanation of the Bermuda Triangle. That, and can you say, has anybody ever noticed that there are hurricanes in the Bermuda Triangle? Let's talk about missing airplanes before there was good weather forecasting, and you fly through the Bermuda Triangle. Think about that. I wonder if there's a high incidence of lost flying machines and ships, boats. It's because of lack of weather. Nowadays, there's a lot better stuff. All right, so deviation. So deviation is a magnet that's either in the airplane or it's near the airplane that causes it to read incorrectly. Now, in the airplane, what are you talking about, Mr. Johnson? There's magnets in the airplane? Why, yes, there are. What if there's a piece of steel? Any piece of steel can be turned into a magnet. Take a magnet and touch a piece of steel, and then you hit a hammer on that steel and take the magnet away. Some of that steel will retain some of the magnetism. You can actually turn it into a weak magnet. It won't be as strong as the original magnet. Also, if you push electricity through a wire, electricity going through a wire turns the wire into a electric. Do you think there are wires inside that has electricity going through them? A couple of them, maybe 20, maybe 100. And guess what is going on inside of the airplane radios that are right underneath the compass? Is electricity going in? On the inside of an airplane radio? Maybe you haven't seen an airplane radio. I have. I'm going to tell you the answer is yes. Airplane radio. If they're and tell you what, if you're in an airplane and you turn the starter switch on, the magnetism, you just turn to the starter into a really, really, really strong magnet. I'm telling you, if you're the compass while you're starting the engine, which you pretty much never do, you're going to see the compass turn. In flight, not very often. So somebody can take that into account, and I'm going to show you a slide here. So here's this compass rose. So what somebody does is, in fact, when that compass rose out there outside was painted, it's extremely accurate. But it was done I think it was done in 5 or 6. So it might be a whole degree. Radio in it. What you would want to do as the mechanic is calibrate the compass. It's also called swinging the compass. Right? Either of those turns down. The airplane up with somebody with the engine running and the radio's on, and somebody on the outside at the compass rose telling the pilot to turn left or right, or the other mechanic to turn left. Get that airplane lined up. Every 30 degrees, the airplane's lined up on 360, and they look at the compass and say, aha, it says 358. It's off by 2 degrees. And then they'll line it up at 030, and they'll look and say, oh, the compass says 028. It's off by 2 degrees. Then they'll line it up at 60 degrees, 060, and the compass will say 057. Oh, that's 3 degrees away from what it's supposed to be. And they'll do that all the way around, and they'll take this information, and they'll put it on a compass correction card, which hopefully I have a picture here. Ta-da! So you'll notice that this one, nobody does this anymore because nobody has airplanes where they don't use the radio. But it says if you want to fly a magnetic heading This is all magnetic because we're talking about the compass, right? So we're going to do everything in magnetic. If you want to fly true north, 000 is the same as 360 because there's 360 degrees in a circle. It says we're not going to worry about the radios off. If you've got the radio on, you should fly so the compass says 001, but you're really flying 000. You notice here it's off 2 degrees, 2 degrees. Look, here's off by 5 degrees. So if I want to fly a magnetic heading of 09 or 0, I actually have to fly so the compass shows 095. And in this case, they say steer. If I want to fly 090, I need to steer so the compass says 095. So that's 5 degrees off. And this is a document that's in the airplane. The airplane is not legal to fly unless that's in the airplane. And technically, when you calculate all that 077, we talked about going to Las Vegas, and we said, let's say we came up with the magnetic heading of 077. We'd have to look right in the middle here and say, you know what, that's between 2 and 5 degrees off. I'm going to call that 3 degrees off. I'm going to have to, you notice this is bigger. You know, we started with 090. We subtracted 13 for variation. Now what we have to do is, look, we have to add 3 more degrees because we're about halfway between 060 and 090. We're going to have to add 3 degrees, and now we're going to have to aim for 080. Now the good news is that 5 is a pretty big number. Most of the time these numbers are 1 or 2 or 3, and you've got other ways to navigate. But let's just say you're navigating by a system called dead reckoning. Has anybody ever heard of dead reckoning? Okay, dead reckoning means that all you have to navigate is your clock and your airspeed indicator and your compass. And you calculate. So here's a quick one on dead reckoning. Let's say you're going 60 miles. Here, I'm going to ask somebody on a popsicle click. You're going 60 miles an hour. You drive for 60 minutes. Drive for 1 hour. How far have you gone, Karen? 60 miles. Okay. So it's not that difficult to calculate how far you went. Just for fun, let's try it again. You're going 60 miles an hour, but you travel for 30 minutes. For a half an hour, Johnny, how much? Went for a half of an hour. Not twice as much you need in time. You're going 60 miles in an hour. How far do you go if you travel for a half of an hour? 30 miles. Right, okay. So if we're reckoning, that's the math you would do. So if you practice at it, you get good at it. We're going to use actually a mechanical calculator to do it. So if I say you're going 78 miles an hour, yeah, well, 28 goes into 78 about 3 times, so that's about a third of the distance, so you'd go about a third of 78, which is about 26 miles. But we got a little calculator to figure it out. It's probably 27.2 miles or something. So that's how you can calculate how far you went. But now the issue we're talking about here is what direction you're going. If I want to go from Selma Airport to San Francisco, and I'm going to pretend that I can't look out the window and use landmarks, I have to know how far to turn left and how far to turn right. So we would measure on our chart our true course off of those lines. We'd apply the magnetic variation. And then if we knew what airplane we were going to go fly, or once we got in the airplane, we'd look at that magnetic heading, and then we'd say, oh, we got to add 3 degrees to it. Now, if there was no wind, we could fly for a certain number of minutes and be able to look out the front, and San Francisco would be pretty close to where we thought it would be. And we're not going to get into it now, but there's also a way to calculate the effect of when you left, or blowing coming from the front and slowing you down, or blowing from the back, a tailwind, and blowing you forward. So the reason I'm diving into all this stuff is because you need to understand this if you're going to be a decent private pilot. I don't know, does anybody want to be an indecent private pilot and go streaking? Oh, everyone raised their hand. Okay, good. Alright, so let's see how much I've got covered here. Alright, so those are the errors. And I want to look at next is magnetic dip. Has anybody ever had magnetic dip? My personal favorite, I have two dips that I enjoy the most with potato chips or corn chips. I like homemade guacamole, especially if you make it with just, avocados that are just ripe, and you chop up your own tomatoes, and you chop up your own onions, and you put in some lime juice, and you put some cilantro really fine, and then just a little sour cream. Not a lot. I'd say less than a fourth of the whole thing is sour cream. So it's 3/4 avocado and 1/4 sour cream. So it's still mostly sour cream. That's what I'm talking. Oh, and then there's a plethora of choices about hot sauce. If Joshua Garcia Cholula was here, I would say that Cholula was my favorite hot sauce. There have been times, there was about a 3-year period when I made guacamole, I always used Cholula hot sauce because it was reasonably hot and I didn't have to put a lot of it in there. However, there's two other kinds of dip. One of them is, my favorite is toasted onion with Lay's potato chips or Ruffles. Anybody ever had toasted onion dip? There's also green onion dip, but I think the toasted onion dip is better. And then there's magnetic dip. Dip can be made either with guacamole or with toasted onion. And that's where the recipe is identically the same, except you drag a magnet through the dirt with a string and you pull it up and it's got all those little black things on it, those iron filings. And so now they're a little bit magnetic because they've been touching the magnet. You scrape them off with a fork into the dip and stir it around. So now you have magnetic dip. If you eat enough of it, you can put little pieces of iron up next to your stomach and it sticks. Has anybody ever tried that? Am I the only one that's ever tried that? Okay, I guess I'm the only one that's ever tried that.
Hello again and welcome to another Fly the Wing 5-minute in-flight maneuver video. This month we're going to review the very exciting magnetic compass and all its errors. You'll find a compass on virtually every airplane from the smallest 2-seat trainer to the largest jumbo jet airliner. It's the one instrument that needs no electrical, static, or vacuum system to function. But there are some inherent attributes related.
So listen to what he just said. It doesn't need electricity. It doesn't need vacuum. It doesn't need static pressure, torpedo pressure. This is wonderful about the magnetic compass that I'm sure you're going to write down, is that it doesn't take any power source of any kind. If you had an electrical system failure, all you'd have to do is turn on your flashlight so you could see it. So we're going to say it doesn't take any power source of any kind. So it's awesome. It's ridiculously simple. It has one moving part, just that one floating around in here, and they're going to show you a picture of it here in a second.
Related to its simplicity that you must be aware of. First, all our charts are referenced to the true North Pole, yet the location...
Check it out. So look at this line here on the left going straight up by the 117. That's pointed to what direction? The true North Pole.
Of magnetic north is really 1,300 miles away. This presents...
So he said it's 1,300 miles. You don't have to write down. But if the true north is right here, look, you can see Alaska on the left, and here's northern Canada, and there's the magnetic North Pole. And every time everybody looks for Santa Claus, they follow their compass. And what do they find? Some polar bears and some elephant seals and a lot of snow in northern Canada.
Presents the first issue. To navigate using a chart designed off of true or geographic north, but with a magnetic compass, requires us to correct for the difference between those two. This angular difference between true and magnetic north is known as variation. Now, it changes geographically. Near Chicago, it's almost non-existent. The true North Pole is nearly perfectly aligned right behind magnetic north. But in Southern California, magnetic north is 12 to 13 degrees east of true north. So we adjust a course plotted on a sectional chart by subtracting 13 degrees from true north, so that our magnetic course in the airplane more directly corresponds to what the compass is going to indicate.
So did y'all write down that east is least thing? And you wrote down the west is best, so calculating magnetic variation, east is least and west is best. Nice thing is that works even when you're on the east coast. Remember, the east is your variation, not your location.
The broken red line on your sectional chart is the isogonic line, and it depicts the amount of variation in your area. The next error common to the magnetic compass is deviation. Deviation is the result of electrical and avionics system and other metal in our airplane. Now, it can change based on the actual heading of the airplane, so the AMT will determine the amount of error on each of the cardinal headings by taxiing the airplane to a compass rose painted on the airport surface and noting the amount of error when the nose is pointed on each of those headings. This correction error, or deviation, is then written on the compass card, which is affixed to the front face of the compass itself. The last two errors we're going to discuss are related to the construction of the compass itself. These are known as dip errors. Now, this cutaway diagram of a compass shows the card floating in a kerosene-like fluid, which helps to dampen its movement. The card has a steel pivot in its center that rides inside a hard glass jewel cup. Now, this all works well with the compass itself. These are known as dip errors. Now, this cutaway diagram of a compass shows the card floating in a kerosene-like fluid, which helps to dampen its...
So we're going to take a look at this for a moment. So what you want to notice is this black thing with the white letters. That's the one moving part, and it floats around. There's actually a pin in the middle of it, and it floats around. It doesn't show it very well, but there's something on top, so if you fly upside down, it can't come apart. If you look at these bellows over here, if you look at
its movement.
If you look at this over here, there's actually air in it, and it's vented.
The card has a steel pivot.
Sorry, it's vented to the outside. So when the fluid in here gets hot, it expands and pushes the bellows, and that way the case doesn't overexpand and break. Or if this fluid gets cold and it contracts and gets smaller, this bellows can move over, and that way the sides of the case don't get pushed in. So I guess one could argue there's actually two moving parts. There's this compass card that rotates, and then there's this bellows that expands and contracts. But some people might argue that the bellows isn't really moving. One could argue it's not a moving part.
Pivot in its center that rides inside a hard glass jewel cup. Now, this all works well in straight and level unaccelerated flight. In fact, that's the only flight condition when the compass is truly usable.
So he just said something. The only time the compass is accurate is when you're in straight and level flight. That means you're not turning, and you're not accelerating, decelerating. You okay, Brian? I'm sorry. You have a headache? I'm sorry to hear that. So what you need to do is now, the compass is only circumstances. The airplane is flying straight. You could put in parentheses, no turning. And it's not climbing and it's not descending. And it's not accelerating. It's not getting faster, accelerating. It's not slowing down, decelerating. So the wonderful thing about this compass is that it doesn't have any power source. It just works and works and works and works. You almost never hear of a compass failing. About every time you ever hear of a compass failing, people the compass, and that means it's never hear of that. So it's a really awesome device. It's a really awesome gauge because it's so simple it almost can't fail. But the downside is it's only accurate under this to right and not accelerating or decelerating. As pilots, since we're a lot, we have to understand when is it okay to look at the compass and how weird is it going to look when we're doing one of those things. So now he's going to talk about these two kinds of errors.
The lines of magnetic flux between the north and south poles. This causes a downward deflection or dip of the compass card. In a bank, the compass card dips to the low side of the turn.
Okay, so what he's going to now talk about is magnetic dip errors. So if you have those sheets, one that talks about magnetic dip, is there also just after that it says UNOS, and another one that says ANDS, ANDS, maybe it's on the next page. Yeah, UNOS and. So he's those two slides. So what he's talking about now is the magnetic dip error. So you notice, what's the airplane doing right here? Is it straight and level? Are the wings level? No, the wings are not level. The airplane is turning. And you'll notice it's hard to make out, but in the upper right-hand corner, it says this airplane is headed towards magnetic north.
Giving an incorrect turn indication. This error is most apparent on north and south headings. So when turning from a heading of north, the compass is briefly going to give an indication of a turn in the opposite direction. And when turning from a heading of south, the direction of turn indicated is correct, but the rate of turn of the compass is faster than the actual turn rate. When turning from the north, the compass lags. When turning from the south, the compass leads. You can remember these nuances by using the acronym UNOS, undershoot north, overshoot south.
About is magnetic dip. So I want to draw a picture here. Don't worry, we're going to get back to that video because I know you're intrigued. Enthralled? Could you be enthralled? Does anybody know the difference between being intrigued and being enthralled? Yeah, me neither. Okay, so let's say here's the world, and we're going to say here is the magnetic North Pole. And those lines of flux, they actually start coming out of the Earth and start curving before they get to the magnetic North Pole. And they get really big over the equator and they come back in. So these are lines of flux. And we're talking magnetic lines of flux. So that's what the compass itself, that little card in there, that card looks kind of like this. And it's got the numbers and stuff on it. So it's trying to point that direction. Oh wait, it's actually trying to point in the equator. Exactly at the equator, this line is perfectly parallel. But here in the United States, so he'll just draw the 48 contiguous states right there. Right here, the compass is trying to be, because of gravity, parallel with the surface of the Earth. But look at the line of flux. The line of flux is actually pointing down. So if it wasn't for gravity, this side of the compass card would actually dip. So what happens is when you turn, you're allowing this to dip. So that's this error here, this compass card, this black thing with the white pictures, the white numbers on it. That's what he's going to talk about here in a second. It's called magnetic dip. I'm going to go back just a little. So there, that's what a compass looks like. And you notice, look at the bottom of that. You can see the compass card. You can see half of the compass card.
So when turning from a heading of north, the compass is briefly going to give an indication of a turn in the opposite direction. And when turning from a heading of south, the direction of turn indicated is correct, but the rate of turn of the compass is faster than the actual turn rate. This is a downward deflection or dip of the compass card.
Okay, so let's look at this airplane. It's flying towards, it's hard to see it right at this moment, but it's flying towards the North Pole, towards the magnetic North Pole. It starts a turn. That's going to allow the front of that compass card to actually twist, in this case, twist to the right or dip down. And so it's going to show a turn wrong. Because this airplane, if it's turning right, the compass ought to move in the opposite direction. So when it says undershoot north, it's telling you that you need to undershoot whatever that compass is reading. Because it's, did I get that right? Undershoot north? Okay.
In a bank, the compass card dips to the low side of the turn, giving an incorrect turn indication. This error is most apparent on north and south headings. So when turning from a heading of north, the compass is briefly going to give an indication of a turn in the opposite direction. And when turning from a heading of south, the direction of turn indicated is correct, but the rate of turn of the compass is faster than the actual turn rate. When turning from the north, the compass lags. When turning from the south, the compass leads.
So you got that part? That's a review, right? Where you hit that part already?
You can remember these nuances by using the acronym UNOS, undershoot north, overshoot south. When turning to a heading of north, roll out on a compass heading about 30 degrees before your desired course. Anticipate.
So that UNOS is what you need to do. That's saying what you need to do. If you're using the compass and you're turning towards the north, you need to undershoot it. That means roll out of your turn early because the compass is incorrect. And overshoot south. That means if you're turning towards the south, you need to go past the heading you think you need to go to, and you roll out, and then the compass is going to come back to where it's supposed to be. So you need to write UNOS. You need to write down there, this is what the pilot needs to do. This isn't actually describing that last one there with lead and lag. That's describing what the compass does. This is what you as the pilot need to do. Did you know you can go up and fly an airplane in the United States or most other countries, and if it's day VFR, visual flying rules, that is, you're in the cloud, you can see well, hence the term visual. You can go flying, and all you need on the flight instruments is an airspeed indicator, an altimeter, and a compass. You still need an RPM gauge for the engine. You need an oil pressure gauge. You need an oil temperature gauge for the engine. You need fuel tank. The airplane, you only need the airspeed indicator, the altimeter, and you only need two out of the six-pack because the compass is separate from the six-pack. Six-pack and one in the chamber. That's a firearm reference. In any case, 6 plus 1 is what's... There's actually some navigation instruments we haven't got to yet. But yeah, you only need 2 out of the 6 plus the compass. Those 3 things, you're going to fly an airplane or a helicopter in the day, and it's visual flying rules. Actually, technically, at night, under many circumstances, you only need those 3 things, an airspeed, an altimeter, and a compass. Because you're deciding how far to pull the nose up, how far to push the nose down, how far to bank the airplane left or right by looking out the window and comparing your to the horizon of the Earth. You actually end up having more engine instruments because you got RPM, oil pressure, oil temperature, and at least you got to have 1 fuel tank. So you got to have at least 4 other gauges. And all the little tiny airplanes I've flown have two fuel tanks. So that's 5 gauges to run the engine and the gas. Each 3 to operate the airplane. So, but does anybody not understand why understanding how the compass works is reasonably important? I'm telling you, on your oral exam, on your check ride, your examiner is going to ask you compass errors. Probably they'll just say, tell me about the compass turning to north. And you're going to say, oh, well, if I'm going to turn to a northerly heading, I need to undershoot it. That is, I turn before I get to UNOS. And if I'm going to turn close to south, I'm going to overshoot and go past it. And this is a magnetic dip error. There's 2 magnetic dip errors, and making turns towards the north and making turns towards the south is one of them.
before your desired course, anticipating that lag. When turning to south, roll out after the compass turns to a heading about 30 degrees more than your desired on-course heading to account for the lead of the compass. The final compass anomaly we'll discuss are acceleration and deceleration errors, which are really nothing more than the effect of inertia on that compass card, which is pivoting on top of a jewel cup. If the airplane accelerates on a heading of east,
Okay, so I would like you to write down that the acceleration and deceleration errors are due to the inertia of the compass card. Inertia is spelled I-N-E-R-T-I-A. Inertia. E-I-N-E-R-T-I-A. Let's see. I'm going to see if somebody can tell me what inertia is. Surely there's someone I haven't called on. Surely I haven't called on Shirley. Rodrigo. Inertia is? Have you ever heard of that word? You ever heard something momentum? Here, I'll let you ask a couple of questions, and then I think you know what I'm talking about. You just don't know the right word. Let's say you're in a car going 60 miles an hour and the road is flat, and there's no other cars, and it's on the freeway, and it's a stick shift, and you stick. Have you ever been in a car with a stick transmission? You shift it into neutral, and the engine is still running. Power steering works, and the brakes work. And you don't put your foot on the gas. You take your foot off the accelerator pedal. Do you stop immediately? No. What happens to the car? It starts slowing down. Okay. Stop immediately, and your head hit the windshield. Okay, that's all right. So let me ask a different way. So you're in this car. You put it into neutral. You take your foot off the pedals. The car starts slowing down. Okay. The car doesn't stop immediately because there is energy in the car. If somebody ran out in front of you, it would hurt them, yes? Okay. Where does this energy come from? It's because of two things. How much does the car weigh in pounds, and how fast is it going? If somebody hits me with a bicycle that weighs 25 pounds, and they're only going 10 miles an hour, it will hurt, rupture my spleen, and I probably won't die, correct? Okay, that's because the weight of the bicycle times the speed, weight times speed, equals the energy stored in the bicycle. This energy stored in the bicycle is called inertia. Or inertia, it's the same thing. If I have a car that weighs 3,000 pounds and it's going 60 miles an hour and I hit somebody, will I give that person more energy? Yeah, the car has a lot more energy because 3,000 times 60 is a big number compared to 25 pounds times 10. So the bigger something is, the more inertia it has. And the faster it's going, the more inertia it has. So now you have a word. So that little black compass inside the compass, it has a very, very, very small amount of inertia. But it's really easy for it to wiggle around. So when he says the error going east and west is due to the inertia of that compass card, the fact that the card wants to keep doing what it's doing until you just try to stop it. It's like a car. If you let off the gas and put it into neutral, the only thing stopping it is the tire resistance on the road, the inside of the wheel resistance, and the air resistance. So that's all trying to make the car slow down. So that's counteracting the inertia. But it'll take a little while. You might be able to go 1,000 feet, 2,000 feet, if it's perfectly flat. You got really skinny tires, and you pump them up to 150 pounds per square inch. You could go for a long time. Does that help? Does anybody not know what inertia is? So he's talking about, I'm going to back up, he's talking about the inertia of that black card right there inside of the compass.
30 degrees more than your desired on-course heading to account for the lead of the compass. The final compass anomaly we'll discuss are acceleration and deceleration errors, which are really nothing more than the effect of inertia on that compass card, which is pivoting
The inertia of the compass card
on top of a jewel cup. If the airplane accelerates on a heading of east, the inertia of the weight holds the float back and the card rotates toward north. As soon as the speed of the airplane stabilizes, the card swings to its correct east indication. Flying east and decelerating, the inertia causes the weight to move ahead and rotate towards south until the speed again stabilizes. The same thing happens when heading west. A great memory trigger for these errors is ANDs. Accelerate north, decelerate south.
So this is the same error whether you're going east or you're going west. So I'll give you a second to write that down, and then I want you to write down something else. So that's what ANDS stands for. Accelerate north, accelerate south. And you can write down, this is describing what the compass does. Going east or west. So this is east-west. So this only applies if you're flying east or if you're flying west. If you're flying north or south, the compass card will wiggle back and forth, but you're already aiming towards north or south, so it doesn't do anything. So if you're going east, from 100 knots to 100 knots, you're accelerating, and the compass is going to point farther north than it's supposed to. So let's just say for fun, I'm taking, and they're pointed 0 towards the coast of the United States. 090 magnetic. And then I let go of the brakes, and I accelerate from 0 to 60 miles an hour before I lift off the ground, before I rotate. Which direction will the compass move? Yeah. I'm going east or west, and I accelerate, even though I'm not. I don't lift off. I slam on the brakes. I tap into the far end of the runway. I turn around, and now I'm aiming 270. I'm aiming west, magnetic west, 270. And I do the same thing. I hold the brakes. I'm at 0 miles an hour. I push the throttle up. I let go of the brakes, leave the throttle up, and I accelerate from 0 to 60. Am I going east or west? I'm going due west. I'm going west at 270. Am I going east or west? Yes, I'm going either east or west. So I'm going to have easterly or westerly acceleration errors. If I'm accelerating, what is the compass going to read? Even though I'm not turning, the compass is going to make it look like I'm turning towards the north. Okay, let me back up. Let's say I get up to 60, and it says that I wait for about 10 seconds. I pull the throttle back a little, and I'm cruising at 60. So anyway, the compass comes back to 270. Now I pull the throttle back all the way, and I slam on the brake, and I decelerate to 0. Which way is the compass going to look like it's turning, even though I'm not really? I'm not going to do that today. The next time we're on a simulator, we're going to get the magnetic errors so you can see what it would actually look like. So we're going to finish this video.
When you accelerate the airplane, the compass indicates a turn toward north, and when you decelerate, it indicates a turn toward south. Well, we just covered a lot of technical information related to the airplane's magnetic compass. For more, review Section 7 of the Pilot's Handbook of Aeronautical Knowledge. Then observe how these errors actually occur in your airplane.
That's enough for one day.